All right, how's it going, everyone? My name is Nikhil Trivedi, or DC Area WX on Twitter, and today I will be giving you guys my 2023 Atlantic hurricane season forecast. Today, we're going to start off with the numbers, which you're currently seeing on the screen right now. Then I'll talk a little bit about my accumulated cyclone predictor model thing, and then the rest of the video will be dedicated to my forecast methodology, like the reasoning that goes behind my forecast to prove to you that I am not just putting this in a random number generator. I do try here, even if the forecast doesn't end up so hot. Before we get into anything else, let me just preface this by saying that I am just a college meteorology student. This is by no means an official forecast, and for official information, visit NOAA and the National Hurricane Center. So without further ado, let's just start off with these numbers. So as you're seeing on the screen right now, I'm forecasting 13 to 16 named storms, 6 to 8 hurricanes, 3 to 4 majors, and 120 to 140 accumulated cyclone energy. All of these numbers are slightly above average for the 1991 to 2022 average. So I'm forecasting a slightly above average hurricane season here. If you take a look at this graphic, this shows my ACE predictor model output essentially. How this model kind of works is it correlates different atmospheric variables, things like sea level pressure, sea surface temperatures, and it correlates that to hurricane activity in the Atlantic. And it uses those correlations to come up with a prediction for ACE, which is a really good metric for overall hurricane activity. So this year, this is forecasting 138 ACE in the Atlantic, which puts it in the upper end of my own range. So it sort of aligns with my thinking, though it's more aggressive than I am willing to go at this point. I will say this did not perform well in the Atlantic at all last year. But to be fair, no forecast really performed well in the Atlantic. It was just a much less average season than we were all expecting. It did perform pretty well in the Eastern and Western Pacific Basin, so I'm hopeful that this year we'll have better results, hopefully. So that's just going to be a wait and see situation. And with all that out of the way, let's just get right into my methodology. I'm forecasting an above average hurricane season to restate that. So from where we're going here, I think the best way to look at this is going to be to look at this sea surface temperature correlation map. What this does is it correlates ocean temperatures to hurricane activity. Um, in the blues, you'll see that cooler ocean temperatures correlate to enhanced hurricane activity in the Atlantic, and in the oranges, warmer ocean temperatures correlate to enhanced activity. So here you see two big regions of correlations, and these are the two regions I'm going to be talking about the most today. The first one is the ENSO, where you see a solid La Nina correlation with these blues starting off near South America and extending through the central equatorial Pacific. And in the Atlantic, you have a big horseshoe of warmth, which correlates to activity from the North Atlantic through the Canary Current and into the tropical Atlantic. Finally, you have this little sliver of coolness from the Baja to Hawaii that also correlates. It's a much weaker correlation, but I will be talking about it at the end of the video. So let's first start off with the ENSO. So for the past 3 years, we've been in pretty much unabated La Nina conditions, but clearly that is not the case this year, with a fairly substantial El Nino event already present in the eastern equatorial Pacific. You have really warm anomalies, 2, 3, 4 degrees Celsius above average right off South America, and then fairly widespread 1 to 2 degrees Celsius above average throughout the eastern and central Pacific. The reason this thing came on so fast, or at least one of the reasons, is thanks to all of the warm water that piled up in the Western Pacific, thanks to those enhanced trade winds during the La Ninas. You just had 3 years straight of really strong trades, which piled up a big warm pool just below the ocean surface in the Western Pacific. You can kind of see that here in this top graphic. Top graphic is from the fall of this past year, and the bottom one is current. What this essentially shows on the x-axis is averaged ocean temperature anomalies across the equator and along the Pacific. So the easternmost part of this graphic right here is the Eastern Pacific, and you go westward as you go left, and the westernmost portion is the Western Pacific. On the y-axis is ocean depth, so you start off at the surface at the top, and as you go down on the graph, you go deeper into the ocean. So right on around 100 to 200 meters below the surface in the Western Pacific, around the equator, you had this big time warm pool just sitting there waiting to be unleashed. It's been sitting there for a while. It's been there for 3 years now, and it's just grown in magnitude as more and more warm water has piled into it. And we just needed something to pull it eastwards. And we finally got that something this March when we had a couple big time MJO passes, which helped to pull this whole thing eastward. And now what we're sitting with is a big time warm pool, not only in the Western Pacific, but extending all the way to the surface of the Eastern Pacific. And in fact, you have really high magnitudes just below the surface in the Eastern Pacific. Interestingly, some of the warm pool has remained in the Western Pacific. Usually, you would have expected this whole thing to move eastwards and then to be replaced by cool anomalies, but this is a little bit abnormal. But other than that, this is a very impressive El Nino that's come on very quickly. The reason El Ninos inhibit hurricane activities for two main reasons. The first one being that all the warm water here tends to create more thunderstorm activity and convection in the Eastern Pacific because you have more instability and it's just easier to fire free convection with that. All the outflow from that convection tends to get wafted into the Atlantic Ocean in the form of upper level westerly winds. And when you have easterly waves clashing with upper level westerly winds, you tend to lead to a lot of wind shear on those waves. And that's one of the main reasons why the Western Atlantic shuts down, especially during El Ninos. The Eastern Atlantic tends to not be affected as much by that aspect. The other big issue, this one does affect the Eastern Atlantic more, it affects the entire Atlantic, is that your whole global circulation pattern gets kind of messed up. You have, again, all of this warmth and all of that convection leads to general background rising motion across the Eastern and Central Pacific. One of the places you'll then develop sinking motion is the maritime continent right over here, but the other place you'll develop it a lot of times is the Atlantic basin. And when you have background sinking motion, it's just harder to sustain thunderstorms and convection because those inherently rely on rising motion. And if you're in background, you're not allowing for that. It's just harder to generate them and therefore harder to generate and sustain tropical cyclones. So if this was the only factor, yes, this would be a very easy below average hurricane season forecast. But clearly, this is not the only factor. Let's take a look, another look at that correlation chart. The other big, arguably bigger correlation region is this big horseshoe, what we call the positive AMO. So this is the correlation, and this is our current configuration. Very, very similar. Where you have warmth extending from Greenland, just south of Greenland, through the Canary Current over here, and very warm anomalies in the main development region and tropical Atlantic. So warm, actually, that a lot of this is record breaking warmth since the Coral Reef Watch dataset started. If you take a look at this graphic, everything hatched here indicates record warmth for this time of year. This entire chunk of the North Atlantic, parts of the Canary Current, and essentially most of the tropical Atlantic is all at record warmth. So not only are we in a positive AMO, we're in a really impressive positive AMO. What this does in the MDR is when you're warmer than average, you have more energy for tropical cyclones to feed off of. You have more instability for thunderstorms to fire, and it makes it easier to develop tropical cyclones. And it also implies background weaker than normal trade winds, which imply weaker than normal wind shear. All these things very favorable for hurricanes. Now, this is not the only area where correlations occur, however. Remember, there's a big chunk in the North Atlantic and in over this Canary Current region. The reason this Canary Current is such a big correlation, not just the main development region, is because it promotes longevity of the warmth in the main development region. What I mean by this is waters in the Canary Current flow southwards off the coast of Spain, off the coast of Africa, and into the main development region. If this area is warm in June, This water over the coming months translates down into the main development region. So if you're warm in June here, you're probably going to remain warm in the main development region for peak hurricane season. And so I feel very confident that we're going to be dealing with a substantially warm main development region along with the substantial El Nino event we have. So all of a sudden here, you're seeing two big time conflicting factors. And I'm very confident that both of these will be very not only present during the peak of hurricane season, but quite powerful during the peak too. So I could honestly just say these things are going to cancel out and call it an average season, but that's pretty lame. So I'm going to pick a side here and take above average. The reason I feel confident enough to do this is for some of the climate model output. The NMME is essentially an ensemble of a bunch of climate models and generally one of our better performing ones. So what this shows for on average for July, August, and September is kind of what we've been talking about. Big time El Nino event, big time positive AMO in the Atlantic Ocean. But the third thing this shows, and the one that is going to be the tiebreaker for me, is what we see in the Northern Pacific over here. This is kind of a horseshoe like the AMO, except it's the opposite configuration with cool anomalies and a warm blob in the middle. This is what we call the negative PDO. And what this tends to do when coupled with an El Nino is it dampens the El Nino effect, according to a decent amount of research. One of the many reasons for this is because you're just taking a big chunk of warmth out of the tropical Pacific, a big chunk of warmth that tends to be able to freely fire convection on a daily basis. So if you have less convection in that region, you'll generally have less outflow related shear and less of a detrimental impact on the Atlantic basin. And I think this will help to, I guess, cuff up the El Nino enough to where the positive AMO in the Atlantic will have the opportunity to overpower the El Nino. Additionally, even without that, the Eastern Atlantic just doesn't really get shut down well by the El Nino. And that's also where our most intense anomalies happen to be located this year. So I feel like the Eastern Atlantic will be open for business this year. So we'll just have to wait and see regarding that. And yeah, it's essentially all I have for you guys. Big time El Nino, big time positive AMO. I think the negative PDO could be the deciding factor in whether or not we go above or below average this year. Thank you guys so much for watching. This is my first ever YouTube video, aside from sad attempts in middle school. So just let me know how you think this went. Let me know if you think this is a better format than the blog post so I can see what I want to do going forwards. And yeah, thanks again and stay safe during this hurricane season.